Hi everyone, I will try and do this all in one take, but if I need to edit, I'll do that. So starting with number 21, the question says use theorem 10 to find the curvature, and the function given in 21 is 0 for the I component. Just notice that there is no I component. So then t cubed for the j component and t squared for the k component. And our direction is to use theorem 10, which I'm just going to go back and make sure I have the right formula. It's the curvature formula that we derived in class on Friday. So the magnitude of r prime of t crossed with r double prime of t all over the magnitude of r prime of t cubed. I'm going to do the whole thing on the calculator, so I'll just kind of walk through the defining it and then writing in the command on the calculator. R of t, function 0, t to the third, and t squared. And then for curvature, we're going to do the magnitude of the cross product of r of t, second derivative of r of t, all over the magnitude of r prime of t cubed. So that is our answer. And let's see, it doesn't quite match what I'm seeing in the solutions, but it might just be a different form. So let me check what we have here. T-squared, yes, it is just a different form. Yeah, so what we got here, I'll copy and paste that over, and then I'll write what the answer is in the solution manual, and it should match up. So that's our solution that we got on the calculator. The solution manual shows this answer 6t squared over 9t to the fourth plus 4t squared to the 3 halves. So let's try and reconcile those. It looks like they wrote this as 6t squared over, we'll factor out a t squared from that. So t squared times 9t squared plus 4, all raised to the 3 halves. And 2 times 3 halves gives us t to the third. So we have 6t squared over t to the third times 9t squared plus 4 to the 3 halves. And then those are going to cancel to leave us with 6 over t. Okay, the absolute value comes in there because of the raising t to the 3 halves. We need to have a positive t value there. So, okay, so the formulas match. Good. All right, 23. Same type of problem. So r of t equals 3t for our x component, 4 sine t for our y component, and 4 cosine t for our z component. So that would be a helix. Go back now and just define our function differently. So 3t for the first component, 4 sine t for the second component, and 4 cosine t for the last one. Yes, I copied that right. And then I'm going to just do the same operation again, and I get 4 over 25. So this one is a constant curvature. It is not dependent on t. The curvature is always 4 over 25, which means the radius of curvature is always 25 over 4. Okay, 27. Use formula 11 to find curvature. Okay, so we've got y equals x to the fourth. And if we go back a page or two, I mentioned this near the end of class. We did not derive it. Curvature is the absolute value of f double prime of x over 1 plus f prime of x squared raised to the 3 halves. So let's try and do this one by hand instead of going to the calculator. I think this is pretty doable by hand. Okay, so f prime is 4x to the third, and f double prime is 12x squared. So absolute value of 12x squared, there's no need for absolute value since 12 and x squared are always positive. So 12x squared can be in our numerator. And then our denominator, we have 1 plus 16x to the sixth raised to the 3 halves. And let me check that that matches the solution manual. And it does, so we're good. That's our curvature for 27. Okay, 32. 32 says, find an equation of a parabola that has a curvature of 4 at the origin. and I gave the hint of starting with f of x equals ax squared. Let's see, find the equation. Yeah, and so we're also going to let a be greater than or equal to 0, just as the real mathematicians would say, without loss of generality. Okay, so we'll use the same equation. F prime is 2ax, and f double prime is 2a. So our numerator, our curvature numerator is going to be 2a. We had the condition of a being greater than 0 at the beginning, so we don't need to worry about that. And then 1 plus 4a squared x squared raised to the 3/2. Now we're interested in curvature at the origin being 4. So let's let x be 0 in that formula. So 4 equals 2a over, oh nice, 1 to the 3/2, so just 1. So this means that 4 must equal 2a, and so a would need to equal a 2. All right, so our function would simply be 2x squared. Okay, 38. All right, two graphs A and B are shown. One is a curve, y equals f of x, and the other is the graph of its curvature function, y equals k of x. Identify each curve and explain your choices. Okay, so let's take a look here. All right, so for 38, we've got A in red and B is in blue. All right, so we want to see, is there a place where curvature goes to 0? So it looks like it looks like A is the curvature function and B is the real function. So A is curvature and B is the actual function. That's because when B flattens out, A goes to 0. And let's see what happens at that, where we have a minimum of curvature up where x equals 0, we have a, where x equals 0, the curvature is greatest, which is when a is greatest. So I think that's, check the solution manual. Yes, so that's correct. A is the curvature and B is the real function. For 39, okay, is there ever a place where one of these things looks like it has no curvature? Not really. So neither thing really goes to 0. Well, it does, doesn't it? B could be the curvature because A looks like it's fairly straight at the origin. Let's see, is that right? B is the curvature? Yeah. Okay, so B is the curvature function and A is the actual function in that case. A little bit more of a conceptual question on that one. Okay, 47. Find the vectors t, n, and b at the given point. Okay, so r of t equals t squared, 2/3 t cubed, and t. It's at the point 1, 2/3, and 1, which is clearly then when t equals 1. Okay, so we're looking for big T of 1, big N of 1, and big B of 1. And remember that big B is big T cross big N. Okay, so let's go to the calculator and do it. Okay, so we will define our function as t squared, t cubed, and t. So t of t is defined as the derivative r of t on top over the magnitude of the derivative of t. So now big T at 1 is that vector, 2/3, 2/3, 1/3. Okay, I just checked that with solution manual. 47, big T at 1, very good. Okay, and now big N. So N of T is defined as, oops, sorry about that. the derivative of big T of t over the magnitude of the derivative of big T of t. N of 1 is negative 1/3, 2/3 and negative 2/3. Cool. Negative 1/3, 2/3, and negative 2/3. And then big B is the cross product of those two. So we'll take T of 1 big T at 1 and N at 1. And we get negative 2/3, 1/3, 2/3. Yes. Okay. Did I do it? Find those vectors. Okay, and then 49 is our last problem. And it asks to find the equation of the normal plane and the oscillating plane of the curve at the given point. Okay, so 49 gives us a vector function 2 sine 3t, t, and 2 cosine 3t at the point 0, pi, negative 2. So clearly t equals pi. That's what we're interested in. Okay. Equation of the normal plane. So the normal plane uses big T, and I'm going to write or a scalar multiple of it as its ABC normal vector. So let's find r prime at pi, and then we can just use whatever scalar multiple of it we like to create that plane. Okay. R T defined as 2 sine 3t, t, and 2 cosine 3t. Derivative of r of t gives us 6 cosine 3t, 1, and negative 6 sine 3t. Okay, so that's our derivative. Let's evaluate that at t equals pi. So we get negative 6, 1, 0. Let's go ahead and use that. It's not a unit vector, but that's fine. Negative 6, 1, 0. And so when we use that in an equation of a plane with, remember, this point, it's going to be negative 6 times x minus 0 plus 1 times y minus pi plus 0 times z plus 2 equals 0. You can clean that up. Negative 6x plus y minus pi and equals 0. Let me check that with the solution manual. Y minus 6x. Yeah, perfect. Okay, for the oscillating plane uses big B or a scalar multiple of big B as its normal vector. So this thing is the normal plane. Plane. And then oscillating plane. So we need to find big B as the normal vector. Okay, so I currently have big T. Let's find N. Okay, so N of T is defined as the derivative of big T of T over the magnitude of the derivative of big T of T. And then we're interested in the cross product. The order really doesn't matter because we just want to know we want to use this vector for a plane, but I'll do it the way it's supposed to be. So B equals T cross N. So big T of T crossed with N of T. And if we evaluate that at pi, we have 160. So same deal, we're going to go 1 times x minus 0 plus 6 times y minus pi plus 0 times z plus 2 equals 0. That gives us x plus 6y minus 6 pi equals 0. Let me check that with the solution manual. X plus 6y. Yeah, perfect. Okay, so we did it all, and I did it in one take. How about that? Have a good day, guys. See you tomorrow.